So in this example, what we're going to do is determine whether this data here represents a normal distribution. So for a chemistry experiment, students measured the time for a solute to dissolve. The experiment was repeated 50 times. The results are shown in the chart and histogram. So there are three things that you really want to check to make sure that your data is normally distributed or not. The first is the characteristic that the mean should equal the median. Now, that's in a perfect world. Very rarely when you conduct experiments and collect data will things be perfectly normal. So you want to check, is the mean close to the median or not? So 11.8 is approximately equal to 12. So the first thing we're going to say is the mean is approximately equal to the median. That satisfies one characteristic of a normal distribution. The second characteristic of a normal distribution is that the shape of the graph should be bell-shaped. So if you were to join the tops of each bar, do you get a bell curve? Again, very rarely are you going to get something that is perfect. You're looking for something that is approximately. Is that approximately bell curved? It is. So we have a second criteria satisfied. The graph is somewhat bell curved. The third characteristic is what takes a little bit of calculation because we have to look at that 68 to 95.5 to 99.7 ratio. So we're going to come back up here. And we're going to make note of the mean and of the standard deviation. So the mean being 11.8 and the standard deviation being 3.32. Okay, so the mean is 11.8 and the standard deviation is 3.32. So within one standard deviation, so what we do is we take the mean and we add and we subtract one standard deviation to get the interval. So 11.8 plus or minus 3.32 gives you an interval of 8.48 to 15.12. So 11.8 minus 3.32 is 8.48. 11.8 plus 3.32 is 15.12. If we went up here and counted all the numbers between 8.48 and 15.12, you would get all of these numbers right here. And there are 35 of them. So 35 out of 50 numbers is equal to 70. So 70% of the data is within one standard deviation of the mean. In a perfectly normal distribution, it should be 68. So that's not too far off. Within two standard deviations, if we take 11.8 and add and subtract 2 times 3.32, that would give us an interval of 5.16 to 18.94. So 5.16 to 18.94 would be all of this data right here. And if you counted all of that data, you would get 46 pieces. So 46 divided by 50 is 92. In a perfectly normal distribution, that percentage should be 95.5. So 92 is somewhat close. Within 3 standard deviations, what we'd be doing is taking 11.8 and adding and subtracting 3 times 3.32, and that would give us an interval of 1.84 to 21.76. And then if we look at the data, you can see that all of it is within that interval. So that is 50 out of 50, which is 100%. In a perfectly normal distribution, it should be 99.7. So the ratios of 70 to 92 to 100 are somewhat close to 62 to 95.5 to 99.7. So that's another indication that your data is somewhat normal. So you can write that statement just like this. This ratio is somewhat equal to the typical normal ratios. So because the mean is approximately equal to the median, and because the graph is somewhat bell-curved, and because the ratios that we got within 1, 2, and 3 standard deviations are somewhat equal to the standard ratios, we can say that the data is approximately normal. So that's the process that you need to take to determine whether a piece of data or set of data is normal. The last thing we're going to do in this lesson is to determine a method that you can use to calculate whether a piece of data is an outlier or not. As you should already know, the more data you collect, the more accurate your results are. Sometimes data appears to be skewed due to outliers. The following is one formula that can be used to calculate outliers. It is not the only formula, but it's the formula that we are going to use in this class. So, any number that is less than Q1 minus 1.5 times the interquartile range is a lower outlier, and any number that is bigger than Q3 plus 1.5 times the interquartile range would be an upper outlier. So, the following table illustrates a sample of daily high temperatures in June in Newmarket. So we have 20 different temperatures. What we have to do first is put them into numerical order. Now that your data is in order, we can now find our quartiles and the median. So for the median, we're going to find the nth position. There's 20 pieces of data. So that gives you 10.5. So that means your median is in between the 10th and the 11th piece of data. So the 10th piece of data is 23. The 11th piece of data is 23 as well. So right in between, your median is 23. For your first quartile, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. So 10 plus 1 divided by 2 is 5.5. So that means Q1 is in between the 5th and the 6th piece of data. So 1, 2, 3, 4, 5 is 20. 6 is 21. So Q1 is right in the middle of 20 and 21. So that is equal to 20.5. For Q3, once again, it's going to be in between the 5th and the 6th position. So that's 1, 2, 3, 4. The 5th is 26. The 6th is 26. So right in between, Q3 is equal to 26. The other calculation you need is the interquartile range. And that is equal to Q3 minus Q1. So that's 26 minus 20.5. So that is equal to 5.5. So your lower outliers. Is anything less than or equal to Q1 minus 1.5 times the IQR. So less than or equal to Q1, which is 20.5, minus 1.5 times the interquartile range, and that is equal to 12.25. So anything less than 12.25 would be a lower outlier. There is no data less than 12.25, so there are no lower outliers. For your upper outlier, it's anything greater than or equal to Q3 plus 1.5 times the interquartile range. And that calculation is equal to 34.25. So anything greater than 34.25 is an upper outlier. So this 36, and the 36 is right there. This one right here is an outlier. If you have an outlier in your data, it's up to you whether you want to remove it or not remove it. But whether you remove it or not remove it, you should discuss it in your results. So for instance, if you were to make any kind of descriptive statistics based on calculations, you would say the mean was this, the standard deviation was this, therefore whatever. However, there was an outlier, so that would have an impact on the data. So again, whether you include the outlier or not include the outlier, you should talk about it in your any conclusions. So that completes what we are learning today. If there was anything that you didn't understand, please ask your teacher at the next class. Thanks and bye.